Hello. Now we will study the equipotential surface. So what is this equipotential surface? By definition, locus of all points which are having the same potential is defined as the equipotential surface. So it's a locus of all points having same potential. So locus of all points which are having same potential, they are defined as equipotential surface. So when you join all the points which are having the same potential, whatever kind of surface you will be having, that surface will be equipotential surface. So we'll be getting multiple equipotential surfaces. So I'm calling this S1, S2, S3 and so on. And all the points onto this surface, though I'm drawing a line, but it's not a line, it will be a three-dimensional surface. So all the points which are lying onto S1, they are having the same potential. I call that potential, let's say that potential is V1. All the points which are onto S2, they are having potential V2, and all the points onto the S3, I'm calling that potential as V3. So all points here are having the same potential, all here having the same potential, all points here are having the same potential. So that's how you draw the lines or the surface, equipotential surface. So when you join all the points which are having the same potential, the surface which you get is known as the equipotential surface. Now there are some properties of this equipotential surface. The thing is, since you think about, let's talk about 2 points in this equipotential surface. So since these 2 points in this equipotential surface, they're having the same potential. So between these 2 points or the line joining these 2 points, along the line joining these 2 points, there cannot be any electric field. Because the electric field, the direction of electric field is from higher potential to lower potential. If the potential is same, then along that line, since there is no potential difference which is happening, because electric field, the formula of electric field is minus of dV upon dr. If along dr, there is no potential difference. If along dr, along any dr, if dV is 0, in that case, E has to be 0. So if between these 2 points, if you see, if you take dr along these 2 points, then between these 2 points, dV is 0. So you will find 0 electric field between these 2 points, or you can say, you will never find any electric field tangential to the equipotential surface. Tangential to this equipotential surface, you will not find any electric field. So any electric field you will find that will always be normal to the equipotential surfaces. At any equipotential surface you talk about, any equipotential surface, the field will always be normal to it. The magnitude might vary, like electric field magnitude here as well as here. It might change, we don't care about that. But the electric field, direction of electric field will always be perpendicular to equipotential surface. So direction of E will be perpendicular to equipotential surface. That's the first point regarding the equipotential surface. Along the tangent to the equipotential surface, the electric field is not possible. Okay, so that's first point regarding the equipotential surface. Or basically you can go reverse also. So if you are having some electric field and if you go perpendicular to the electric field, you will always find the equipotential surface. So equipotential perpendicular to equipotential surface is the field, and perpendicular to the field will be the equipotential surface. So there will be no electric field along the tangent to this equipotential surface. Okay, so that's this property of the equipotential surface. Now when we draw the equipotential surface, how we will draw it? The thing is, for that we will take 4 examples. Okay, so corresponding to 4 examples, we will draw the equipotential surface. The first example we will take is the point charge. So if I talk about the point charge. If I talk about point charge, let's say this is the point charge, then corresponding to the point charge, equipotential surfaces are always spherical. So these all are, meaning if I draw any spherical surface, for which the charge is at the center of the surface, then all these are equipotential surfaces, S1, S2, S3. Now why is that? The thing is, if you talk about this point, if this point is at the center of that surface, then all the points onto this surface are symmetric with respect to this charge. If let's say plus Q charge is there, then all the point onto the S1 are symmetrical with respect to the charge. Similarly, all the points onto the S2 as well as S3, they are symmetrical with respect to the charge. So if you replace those points, that there will be no change in the structure. If there will be no change in the structure by replacing the points, it means those points should have the same properties. When we talk about properties, we talk about magnitude of electric field and potential as well. So all the points onto S1 are going to have the same potential because all the points onto S1, they are symmetric. So corresponding to point charge, equipotential surface will be spherical in nature. Okay. Now the second case, if I talk about the uniform electric field, if we are having uniform electric field, now there are many ways to generate the uniform electric field, meaning we can have infinite sheet charge, or if I'm having a point charge and if I go at infinity, so there will be uniform electric field. So if there is a uniform electric field, meaning all the fields magnitude wise they are same as well as the direction wise they all are parallel. If we are having uniform electric field, then the equipotential surface will be planar in nature. There will be plane. All these planes are going to have the equipotential surface. So all the points in this plane. Now this plane has to be perpendicular to electric field. So each and every plane which is perpendicular to this electric field will be equipotential, will construct the equipotential surface. So all the points in this plane are going to have the same potential. And all the points here also are going to have the same potential. I call this V1, V2. So corresponding to uniform electric field, the equipotential surface is planar in nature. Okay. Now, if we talk about third case, if we talk about the infinite line charge. So for infinite line charge. So if I'm having an infinite line charge, in that case, the equipotential surface will be cylindrical in nature. There will be multiple cylinders, obviously, not just one, because there will be multiple equipotential surfaces. So if we draw the cylindrical surfaces, for which the line charge is passing through the axis of that cylinder, axis of those cylinder, in that case all those cylindrical surfaces will form the equipotential surfaces. So this S1 as well as S2 as well as S3 will also come. They will be equipotential surfaces because you see all the points onto this sphere, obviously onto the curved sphere, curved surface only we are talking about. We are not talking about this flat surface, only the curved surface. Okay, so all the points onto the curved surface, they are symmetrical with respect to this line. If you keep changing those points, if I look at one point here and one point here, if you exchange those 2 points, there will be no difference which will be happening into the system. Since there is no difference which is happening onto the system, it means both the point should have the same property, meaning they should have the same potential. And the locus of all those points is defined as equipotential surface. So corresponding to the infinite line charge, cylindrical surface will form a equipotential surface. Okay. So just like that, if I'm having, this time if I'm having a spherical shell or a spherical body, solid sphere. So if I'm having a spherical shell or a spherical solid sphere, spherical body, and as you can see, again, symmetry, all these spherical surfaces, all these equipotential surfaces, they are symmetrical. So if I'm having a spherical body, which is uniformly charged, in that case, I'm going to have more spherical surfaces. So all these spherical surfaces, they will be equipotential corresponding to this spherical body. They are going to have the same potential. So this can be spherical shell as well as spherical body. If there is a charge here, then all these surfaces are going to be equipotential. And as you can see, here also the electric field going to be perpendicular. That's what we learn. Here also electric field is going to be perpendicular to equipotential surface. Here it is already perpendicular, and corresponding to point charge, you know, corresponding to Coulomb's law, electric field is always perpendicular. So if we know the equipotential surfaces, we can directly judge the value of electric field which is going to be there. At least its direction, we are going to get it. Okay. So that is how we define the equipotential surface. So if we can look for the equipotential surface in the question, then corresponding to that surface, we can decide what kind of surface, Gaussian surface we want to take, and what kind of other surfaces we want to take. If you remember, these are the Gaussian surfaces we took when we were deriving their electric fields. Similarly, here also, here also, here also. Okay, so that's the use of equipotential surface. Okay, there are so many other uses also that we will understand, that we will learn later on. Okay.